Hello everyone, thank you for watching this video. So on today's video I'll be doing question 2 of November 2022 question paper, Physical Science paper 1. So I'm not going to write the entire statement that goes with this question on this small sheet of paper, on this small whiteboard of mine, because I don't have too much space. But what I will do is, as I'm reading this question, I will show it to you so that you can also stop the video or pause the video and read the statement yourself, so that you can understand it so that you can understand it better. So I'm not going to write it here, but I'm going to read the statement. I'm going to explain things so that you can understand what I'm doing here. So this, as I said, this question paper is from Physical Sciences, paper 1, November 2020. So this is question 2, and I'm going to read the statement, explain it, and go forward. So let's get started. So this is question 2. So here, what they're saying, question 2. A 20 kg block resting on a rough horizontal surface is connected to blocks P and Q by a light inextensible string over a string moving over a frictionless pulley. So this 20 kg block is attached on this block P and Q. So P and Q, on this block P and Q, by a light inextensible string, which means this string of ours doesn't stretch, it maintains the same length, and the pulley is frictionless, which is there's no friction there, which will add into lowering the motion of this system. So 20 kg block attached to these blocks P and Q by a light inextensible string, which means does not extend over a frictionless pulley. So there's no friction that is happening there. So there's no friction there. So let's continue. Blocks P and Q are glued together So these two are glued together, which means these were two blocks, but now they were glued together using a glue or whatever that is sticking them together, and have a combined mass M. So both P and Q, after they were glued, their combined mass was M. So they are saying a force of 35 newtons is applied on the 20 kg block at an angle of 40 degrees with the horizontal as shown below. So what they're saying, this block of ours is pulled by a force of 35 degrees or 35 newtons. And this force of ours makes an angle of 40 degrees with the horizontal. So as you can see, this is the horizontal, which means now the angle between the force and the horizontal is 40 degrees. That's what they are saying. So this force is pulled, or this force that is applied here at this 20 kg block is at an angle, it is pulled at an angle, not pulled horizontally or vertical to the surface, but at an angle to the surface. That is what they are saying. Also, the 20 kg block experiences a frictional force of magnitude 5 newtons as it moves to the right at a constant speed. So here is what is happening. They are saying this block is experiencing a frictional force of 5 newtons. So this block is experiencing a frictional force, this arrow, so frictional force, this arrow indicates that this force is a vector. So vectors, they have this arrow on top. So this block experiences a frictional force of 5 newtons. So this is on the 20 kg block. So they are saying that the 20 kg block experiences a frictional force of 5 newtons as it moves to the right at a constant speed. It moves to the right at a constant speed. So as much as it is pulled this side, the system is moving to the right, which is in that direction. So this is pulled in that direction, or it's pulled in that direction, but it's still going to that side. So the frictional forces experienced by this is to the right. No, is to the left, because if this system, this block is moving to that side, the frictional force opposes the motion and is going backwards. So which means that this guy is going down, this is going to the right, and the frictional force is going to the other side. So let's go to the first question. Now 2.1. So this is 2.1. First question, they are saying define the normal force. So they want us to define the normal force. So what is the normal force? So I will not write it down here, but I will explain what it is for you and define it to you so that you know what it is. So a normal force is the force that is exerted by the surface on an object, and that force is perpendicular to the surface. For example, I'm standing here in front of you, so I'm on the surface and I'm standing vertically on the surface. So the surface is exerting a force that is vertically upwards, perpendicular to the surface. So in this case, we have this block here. For example, the force here is, let's say you have a surface here and you place an object here. So the surface exerts a force on this object, and that force is perpendicular to the surface, which means it forms the 90 degree, which means it's vertical on a horizontal surface. So if your surface was like this and you have an object here, the normal force, it would be the force that the surface exerting or pushing on this object, and it's perpendicular, which means it will be in this direction, so 90 degrees. So if it's in this direction, the object is here, the normal force here is the surface, surface. So here's the object, the force will be like that. This will be your normal force. All of them will be your normal force. So what I'm saying is, the normal force is the force exerted by the surface, which is, it is applied by the surface on an object, which is placed on the surface. And that force is perpendicular, or it is orthogonal to the surface, which means the force exerted by the surface will always be 90 degrees to the surface. That's what this is. So that's how you define it. You're saying a frictional force or a normal force is a force exerted by the surface on an object, and that force is always perpendicular to the surface. So the surface will not exert a force that is not perpendicular to it. So they will always form 90 degrees. So this is it for question 2.1. So now we move to question 2.2. So now we proceed to question 2.2. So question 2.2 reads as follows. Draw a labeled free body diagram of the 20 kg block. So they want us to draw the free body diagram of the 20 kg block. What is a free body diagram? So a free body diagram is a diagram that shows all the forces that are acting on this object. So it is a diagram that shows all the forces that are acting on this object, or all the forces that are felt by this object, or that are experienced by this object. So first of all, the most common one is force of gravity. Gravity is acting on me as I'm standing here, and it's acting on you as you are watching there. Second of all is the normal force. If an object is placed on a surface, there will always be a normal force acting on it, and it will always be perpendicular to the surface. So the most obvious is gravity because it acts in all of them. So normal force acts on objects that are placed on the surface, because if I'm hanging, the gravity will act on me, but there will be no normal force on me because I will not be standing or placed on any surface. So normal force is the force of the surface on the object, and it's always perpendicular to the surface. So let's draw the free body diagram. What are the forces that are acting here? So you will represent a free body diagram with a dot like this. So the first force that we talked is gravity. This is the force of gravity, Fg. The second force, because it is sitting on the surface here, the surface is exerting a force on this, which is vertical, which is perpendicular to our horizontal surface. So we have Fn, which is the normal force. This is the normal force. Then, what is another one? Another one is the applied force. Because it is applied at an angle, when you are drawing it, you should also draw it at an angle. That means you should preserve the same nature as this one, because the normal force is applied vertically upwards. It would represent it like that. Gravity is acting vertically downwards. It is like that. So even that one should also maintain the shape of 40 degrees to the horizontal. So here is our applied force. Force applied. These are vectors, so there should be arrow on top of them. So this is the applied force. What is the next one? The next one is the tension force. This is the tension force, this is the rope that is caused by the rope. This is the force that is caused by that rope, which is pulled by these guys, which is mass P and Q. And then the last one is the frictional force of 5 newtons that we were told. So because the object is moving to the right, that's what they said in the statement. They said it's moving to the right, which is this one is moving downwards. That means the frictional force is opposing the motion, which is it is on this side. So we have the frictional force here. Frictional force. So this is a free body diagram of this 20 kg block. So these are all the forces that are acting on this block. So this is where I will stop for question 2.2, because they wanted you to show all the forces that are acting on the 20 kg block. So these are your forces. So this is the most accurate free body diagram of or representing all the forces that are here. However, as much as it is accurate and is correct, it is not very helpful when you want to do calculations that are relating to this. You will show this shortly, because when you're doing calculations, you want all the forces, your forces, to be either horizontal with your parallel with your surface or perpendicular to your surface. So this one is not parallel, it's not perpendicular. It is at an angle. So it's not very useful when you want to do calculations. So what I will do now, I will try, let's go to question 2.3. That's why I'm going to try to sort this out, so that it can make things easier for you all the time and be able to perform calculations. So now, let's go to question 2.3. So question 2.3, what they're asking you to do, they are saying calculate 2.3. I'm not going to continue on this slide, but I have information that I need from this diagram. That's why I'm not going to write anything here. I'm going to write it on the next page. Question 2.3. Calculate the combined mass of the two blocks. So they want us to calculate the combined mass M of blocks P and Q. So to perform these calculations, you need to know the free body diagrams of this and that. That's what you need. So we do have a free body diagram for this one, which is that. Now, the next thing that you should do is to find the free body diagram of P and blocks P and Q, which is M. So what you should do first is draw the free body diagram of P and Q. So there are two forces that are acting on P and Q. It's the tension, which is pulling it upwards, and the gravity, which is pulling it downwards. So the free body diagram for M, so this is for the 20 kg block, this one, this free body diagram. So for this one, here is it. So this is the tension, which is equal to that one, but just in opposite direction. And this is the force of gravity, Fg, which is acting on this. So there are two forces acting on this, is this one and gravity. There's nothing on the side because there's no side weight movement that was described. So it's only moving in that direction. So these two free body diagrams are the ones that are going to help us continue going forward into calculating that mass. So you need these free body diagrams in order to use Newton's second law to calculate these. So now I'll turn over to another page and do question 2.3 on another page. So on that question 2.3, I'll be using this free body diagram. So you might not really see this, but I'll come back to it in case we need it. So now let me go to another page and write these free body diagrams and work with them and use Newton 2. Thank you. So I've redrawn this free body diagram. This is the force applied, the normal force, the tension force, the force of gravity or weight, and this is the frictional force on the 20 kg block. So here's the free body diagram for the block M, block P and Q. This is the tension force and this is the force of gravity. Also note, no one told you that you need the free body draw the free body diagram for the second block. But if you want to do the calculations involving the force or weights of another block, you need to have all the free body diagrams. So you were not asked to draw the free body diagram for this one. But it's something that you should be knowing, that if I'm doing calculations on Newton 2 related problems, then you need to have a free body diagram. So let me continue. So this free body diagram is nice because this object is moving downwards, as I said there. So all the forces are either parallel, which is similar orientation, because the parallel to the direction of movement, or perpendicular, but we don't have any perpendicular forces. But here, this one, the movement is horizontal. So 1, 2 are horizontal, which is good, and then 2 are vertical, which is perpendicular to the plane of movement. But now we have that one force which is not parallel or perpendicular to the plane of movement or of motion. So what I always advise people to do is try to decompose or break down this applied force such that it is parallel and perpendicular to the motion. So this is how you do this. You break down this such that it is parallel or perpendicular to the motion. So you can see it's going slightly up. So it's pointing in this direction. That means it has a component that is going up and a component that is going to the side, to the left. So that's what you want to do. So let's copy all others that are nice, which is the parallel and perpendicular forces. Perpendicular because they form 90 degrees with the surface. Parallel, they have the same orientation. with the surface. So let's withdraw all other forces. So we are drawing this one. So this is the normal force, Fn. This is the tension force. This is the force of gravity. And this is the frictional force. So, all the forces that we have drawn here are either parallel or perpendicular to the surface. So what you want to do now is to draw this again such that it is either parallel or perpendicular to the surface. So what you do on this one, you decompose it or you break it down such that you have a parallel and a perpendicular, because you can see that it's going, if you look at this arrow here, let me draw it down here. Here this arrow going this way. You can see that it's moving to this direction. And it's also going up as well. Because if it continues to this direction, you see it's moving in the negative y direction, in the negative x direction, and it's moving in the positive y direction. This. That is what is happening there. So if you are to stretch this and make it bigger, pull it upwards, you see that it's moving towards the negative x direction of the Cartesian plane and the positive y direction of the Cartesian plane. So if you can do this, which means you can split it into that and that. So now you can, since this is your applied force Fa, so you can have force applied in the x direction, which is the horizontal one. Or you can have force applied in the y direction, which is the vertical one, and leave this one out. Because these two combined, they make this one using Pythagoras Theorem. Because if you use Pythagoras Theorem of these two guys, you will see that they give you this. Because when when you add vectors, you add them head to tail. So if you can take this vector and move it here, you'll see that Pythagoras Theorem is this one. So let's imagine that you take this one and pull it to this, the tail of this to the head of this, and that head here. You will see that it makes a complete triangle, which is a right angle triangle. So these two both represent that. So what you can do, instead of writing this one, instead of drawing this one, you can draw this FA in the x direction, or you can say horizontal, but it's very long word. I don't want to write that. FAX, you don't need that. And draw another one that goes up. FAY. So these two, FAX and FAY, are these two components of this one. So you don't have to draw this one if you have drawn the components. So if you have drawn the components, the FA, force applied in the x direction, and the force applied in the y direction, you don't have to draw the original one. It's either you draw the components or the original. So I always advise that you draw the original at the beginning, and then when you're doing the calculation, make sure that all your forces are either horizontal or parallel to the surface or perpendicular to the surface. Then from here, you can be able to do calculations. So now the next step that we're going to do is to perform the calculations, because all our forces are parallel to the surface or perpendicular to the surface. So even if you draw this free body diagram, you will be given full marks instead of that one, because this one and that one are considered as the same as one force, because when you combine them, I said if you take this one and put it here, you can see you have a right angle triangle. So when you do Pythagoras theorem of this one, we will give you that, which is the applied force. So it is the same force. So I always, in my school years, I was using this one because this one was helpful for me to do calculations. So now, what we're asked to do is find the mass of M. That's where we're going to start doing the calculations. But if you don't really understand what is happening here, it's going to be hard to perform those calculations. You don't have to do this if you know in mind that you must decompose this into parallel and perpendicular, because you don't have to draw it like this. But it's easier if you draw it like this because it will help you. So I'm going to the next page. On that page I'm going to only draw this one and that one, because these are the free body diagrams that I'm ready to use that are going to help me perform the calculations. So let's go to question 2.2. So I'm only going to take this one and that one. So this one I'm not going to use because it's not very helpful for me. So you can take it if you know you want to do it. So let's go to the next question. Okay, so I've redrawn this diagram. So what you can see here is this is the free body diagram for the 20 kg block, and that is the free body diagram for the mkg block. We want to find the mass of this unit. So I've explained how we arrived into these free body diagrams in the previous video. So there's no need for me to do that again. So now, what you use here, you use Newton 2. Newton 2 is as follows. F net is equal to ma. So force is a vector and the acceleration is a vector. So what Newton 2 is saying, a net force that is acting on an object will cause an object to accelerate. So the force, all the forces that are, the sum of the forces or the resultant force acting on an object will cause an object to accelerate. And that object will be accelerating in the direction of the force. So if the net force, so the net force acting on an object will cause an object to accelerate in the direction of the force. So the magnitude of the acceleration is directly proportional to the net force and inversely proportional to the mass, which means that the magnitude of the acceleration increases at the similar proportion, at the same proportion as the net force, and inversely proportional to the mass of the object, which means the higher the mass of the object, the smaller the acceleration, and vice versa. So that's what this says. So, which is the sum of the forces is equal to the product of mass and acceleration. That's what Newton 2 is saying. So the net force acting on an object. So the force is the cause. This acceleration is the effect, which means from the sum of forces you get acceleration. So the sum of forces causes the acceleration. So the net force acting on an object will cause an object to accelerate in the direction of the force with the magnitude of acceleration that is directly proportional to the force and inversely proportional to the mass of an object. So the acceleration is directly proportional to the net force, and the acceleration is inversely proportional to the mass, which means now these increase at the same proportion and these ones are inversely proportional. So now the net force. So we can sum all these forces, because the net force is the sum of all forces that are acting on an object. We can sum all of these forces. But I don't like it when you, for example, let's take the vertical forces only. Let's say F net in the y direction of the 20 kg block. So F net in the y, which is in the y direction of the, so this should be y, not x. This is y, this is x. So the sum of forces will be equal to what? We have three forces: the normal force, the applied force, and the force of gravity. So now, what you do, you say the net force is the sum of forces. you add these forces. So you say, okay, we have normal force Fn plus Fa, force applied in the y direction. So these two are going upwards and this one is going downwards, which means they have different directions. So if you made these two positive, this one, if you make these two positive, this one will be negative because it's going to the opposite direction. This one is negative, which is Fg. So you don't have a motion in the vertical direction. So this is not moving in that direction. So it's sitting on the surface, which means these two forces balances out. Which means the sum of these two forces is equal to the sum of those two forces. Which means if they are equal, these two forces minus this one should give you 0. Let me explain it again. I'm saying that you don't have a motion in the vertical direction. Your object is moving in that direction. So since it's moving in the horizontal direction, which means your forces that are here are not balanced. But now, in the vertical direction, you don't have any movement on this one, on the 20 kg block. Which means these two forces are, so the sum of these forces is at equilibrium, which means this object is at equilibrium. It's not moving in the vertical direction. It's still, that means that if you take the sum of these forces, of vertical forces, and the sum of vertical forces, they are equal, which means now the vertical forces equal the upward forces, the sum of these two forces are equal to this one. So if you are saying that these two are equal, that means that if you add these two and subtract them with this one, the answer will be 0 because you said this and that are equal. So if you have them equal, then same thing minus the same thing, which is x minus x is 0. Because you're saying that equation, these two maybe is 5 neutrons and this one is 5 neutrons. So 5 minus 5 is 0. So this plus this equal to that one. So if you say the sum minus the force of gravity, it should give you 0 neutrons. So there's no point in using the vertical forces for finding your net force, because if you're using your vertical forces to find the net force, these vertical forces will cancel out. So to make your thing less complex, only use these forces that are in the direction of movement. So only focus on these horizontal forces, and leave these ones alone. You don't need these ones because they are going to cancel out because you already have the motion there. But if you have the motion in this direction and that direction, then you are going to use all of them. But now your motion is only horizontal, so focus on the horizontal forces only. For example, here the movement is downwards here. This block is moving down, which means now you only focus to the forces that are parallel to the plane of movement or to the direction of movement. So now these forces are okay, you're going to use them. If you had forces in that direction, but there was no movement there, so you're not going to use those forces. So now here is what you should be doing. So now we are going to I'll go to the next page and we do the net and find the net forces for this one, which will be the horizontal forces, and that one, and perform our calculation. So you don't have to use these ones if you don't need to. So you only use them when you need them. If there is a motion or you need to find kinetic friction or dynamic friction or static friction, then that's when you start using them. But for now, you don't need them. So what we're going to do, on the next page, I'll redraw these two and start performing the calculations. So now on this video, I'm explaining everything because I will always reference you to this video when I'm doing, because these questions are similar. I'll meet a question like this down the years or backwards when I'm doing other papers. but I will not explain as precisely as this one. So I will always reference you to this one. So this will be the longest for the horizontal cases. So then the rest I will always explain and then always keep referencing the previous video. So now let me redraw this and perform the actual calculations. So my point was that when you're calculating the net force, don't include the forces that are not in the plane of movement. Only include those that are on the plane of movement. So on the previous free body diagram, where you had the normal force up there, it was going to be tricky because what were you going to do with that force? Nothing. So there's nothing much that you're going to do with that force. Because you will see that you say, okay, someone was going to say, okay, it's not in the plane. It's not in the plane of movement. So I'm going to leave it out. Yet it has a component which is in that plane. So that's why I prefer this one, because this one shows you all the components that you need. Okay, so now what we are going to do is finding the net forces. So we said F net is equal to MA. So F net is the sum of forces. It's equal to the product of mass and acceleration, which is Newton 2 by definition. So now, what we do here, we said that we're going to sum the forces that are parallel to the plane of motion, which is these 1, 2, 3 forces. So now, when you do this, you have to decide with the signs. So what I always do, I assume the direction in which the system is going as positive, and then all forces that are operating in the opposite direction of the motion of the system, I take them as negative. So we said this one is moving to the right and this one is moving down. So the right will be positive, all the forces to the right will be positive, all the forces down here will be positive, and then all the forces that are opposing the motion will be negative. So here, which means in this case our tension is negative, is positive. Then these two are negative. So now for the net force, which is this part, you have, okay, you are summing your forces now. So we have the tension force plus negative frictional force plus a negative force applied in the x direction is equal to MA. This is for the 20 kg block, this one. So now, to simplify it, you say, okay, T minus frictional force minus FA in the x direction, which is horizontal, is equal to MA. So this is the equation for the net force for the 20 kg block. So same thing for that one, for the m kg block. F net is equal to MA. So you are going to sum your forces, which is now, this one will be positive because the system is going down, which means FG minus tension, sorry, corona, tension is equal to MA. So you can say plus negative tension, which is equal to MA. So this one, FG minus tension is equal to MA. So here is your sum of your net forces. So you have these two. What they want you to find, they want you to find the mass of that. So now we proceed with the calculation. So we have managed to set up these two equations. So now let's continue with our calculation now. So to continue with this, let's do this. So it's 2.3. So now we know that T minus frictional force minus what is it? Minus FA, first force applied, which is the X component, is called MA, and FG minus T is equal to MA. So this is the first one is for the 20 kg block, and the second one is for the M kg block. So what I would like you to know, to keep in mind here, you were told that question that the system that is moving at a constant speed. You're told that it's moving at a constant speed. If you notice there, that constant speed is even highlighted in capital letters. What that means is, if your system is moving at a constant speed, that means it is not accelerating. So, which means the speed is not changing. What acceleration is the rate at which velocity changes. Which means how much is your velocity changes. Can be decreasing, can be increasing. Which means here, if they say constant speed, which means they say there is no acceleration all the time. That's what this means. So if you're told that it's moving at a constant speed, know that the acceleration is 0 meters per second squared. And if this is the case, and if the acceleration is 0, you know that F net is equal to MA, but you know your A is 0, which means your F net is equal to M times 0, which means your F net is equal to 0 newtons. So we know from constant speed, if you're told the speed is constant, acceleration is 0, and the net force is 0, which means we have 0 in both of these positions. So we have 0 here and 0 there, which means the sum of these forces goes to 0. And the sum of these forces goes to 0 because it's the system, or the velocity is constant for the entire system. So now we are very close I'm just setting this up. On the next videos I won't be doing all this for similar question. I'll only be doing the questions. So I told you that on your applied force, you can split it into this component, which is Fx, and that component, which is Fy. So now, this is your Fay, Fax, this is your Fa, your original force. You have your angle here, theta, which is 40 degrees in this question. So you can find this, the value of this force and the value of this force using the trig functions. For example, this one, you are given the original force and the angle. You want the adjacent. This is cos. So cos theta is called opposite adjacent, which the adjacent is Fax over hypotenuse, which is Fa. That means now you want to solve this cross multiply. Fax is equal to Fa cos theta. So that's how you find this, the value of this. So you know Fx or Fax is equal to Fa cos theta. Fay is equal to Fa sin theta. So when you're performing the calculation and you have used Fx, this is what you put in the place of Fx. So you have the force applied, you have the angle with the horizontal. Same thing, if you want to use this, this is how you this is how you do it. So I'm going to the next slide where I'm going to continue with this and that. Because what I don't want to do, I don't want just to be solving the questions. I just want to explain them to you so that in future you know what you're doing. So what I'm going to do now, I'll take this equation and this equation and place the zeros there. And instead of this, I'm going to substitute this, the equivalent of this, and perform the calculation and find the mass m. Then I'll be done with this question. Okay, so I just copied these two equations and those ones. So we'll do the calculation now. So what they want us to do is find the mass of the block. You know, you still remember the question. You can go back if you've forgotten. So what you do here, the tension, you're not given the tension. Let's use this first equation. So the tension you're not given, minus frictional force, okay, minus FAX. FAX is this, which is, you put FA cos theta is equal to 0. So now you don't have tension minus frictional force. They said frictional force was 5. FA minus FA 35 cos 40 degrees is equal to 0. So from this equation, you will solve for T. So punch this on the calculator. Negative 5 minus 35 cos 40. So you have T minus 31 comma 81 is equal to 0, which means then you can transpose this to the other side, which means your tension is equal to 31 comma 81 newtons. This is your tension. Now you go to your second equation. Second equation, you have Fg is minus T is equal to 0. Fg is the force of gravity. To calculate the force of gravity, it's simple. It's Fg is equal to the mass times gravity, which is 9,8. So now, there you have Fg minus tension is equal to 0, which is equivalent to saying mg minus tension is equal to 0, because this is gravity. This is how you calculate gravity. And then from here, said okay, mg, in m you don't know m, g is 9,8 minus tension, which is 31,18 is equal to 0. So you can proceed with this to the next page. So you have mg, m times 9,8 minus t, which is 31,81 is equal to 0. So you have 9,8 m is equal to 31,81. So divide by 9,8, divide by 9,8. This cancels out. M is equal to 31,81 divided by 9,8, which is 3.25 kg. So this is the mass of that unit. So this is how you do that question. So this is the end of it. So it was straightforward, but I took all this time because I want to make sure that you understand what you should be doing or what is expected of you. That was the point of being slow on the leg. So no, sorry, on that question. So now let's proceed to the next question. So the next question is 2.4. I'll also show the question paper to you. They are saying, at a certain stage of the motion, block Q breaks off and falls down. So this is how, so we had P you had Q there. So now they're saying this one is falling, so you had the entire system. So you remember that first diagram. So they are saying now, or what I can do equivalently is to show you the original drawing. So what they're saying now is that this block is now breaking off. So now it's more like we are removing this block here at a certain stage. You are left with P only, which means now the mass of this unit is becoming smaller at this point. That's what they are saying. So at some point, Q breaks off and you're left with a smaller and lower mass. So here's the question. 2.4.1. How will each of the following be affected when this happens? So they are going to ask us question about this system. What will happen to the system when you remove that mass there? They are saying, what will happen to the tension of the string? So they are asking how much will be the force, which is the tension, the force on this string. If you remove a mass, that means now there's less pulling down power. There will be less pulling down power, which means now there will be less pull on this rope, which means now the force that will be on this rope will be smaller. That means the tension will decrease. That's what that means. So how will each of the following be affected when this happens? The tension in the string. Choose increases, decreases, or remain the same. So when this becomes less heavier or smaller weight, which is the force of gravity, will decrease here, which is the weight Fg. You will have a smaller Fg. If Fg is small, which is now the tension will be a bit smaller. So it will decrease. So to answer the previous question, 2.4.1, right, decreases. So the tension will decrease when tension decreases when the mass becomes smaller. So here's another question. What will happen to the velocity of the 20 kg block? Explain the answer. So the 20 kg block is moving to the right. So now, if you're breaking off this, there will be a smaller pulling down power. The velocity will decrease as well. Because now, the net force of this is in that direction. So, when you sum all the forces, the more dominant force is the one that is moving to that direction. So now, removing this might change the dynamic of this system as a whole, because now the force that is going to that side is not as strong as before, because we have removed the force of gravity, which increases the tension. So now, the velocity of this will decrease, because now the net force will no longer be strongly dominant to that side. So it will be reduced a little. I'm not sure if that makes sense. So let me go and answer it. On the other side, what I'm saying is, velocity decreases. Now, why? The net force will no longer be that F net dominance to the right will decrease. Yeah? Or will decrease, obviously. That might change the direction of the system. So I'm realizing that I've written below this. So what I'm saying is that the net force will dominance to the right, will become smaller, so the velocity will be slower, or it might even be net force might even end up going to the right, which is now changing the entire direction of the system. So this is where this question ends.